just the list of people who are watching at your slide. Can you iconize that? I see me, Clement, Alil Butuk.
Okay.
Yeah, we are seeing it. It's okay.
Great. So good morning, I'm Christine Davies. And so I'm going to tell you something about the properties of low-lying charmonia and bottomonia from lattice QCD plus QED. So thanks to the organizers for giving me this opportunity. So it's a bit of a change of gear from the talks we've been having, because I'm going to talk about states that are well known in the charmonium and bottomonium spectrum. But the point here is to do precision lattice QCD calculations of them, so much more precise than has been possible before, as precision tests of the standard model and tests of QCD and lattice QCD. So we want to use lattice QCD for precision tests of the standard model. We've been doing this for some while, and we're slowly improving the precision that we can get. But also, of course, in that process, we're hoping to look for new physics. Lattice QCD has a lot to contribute to searches for new physics in weak interaction decays, for example, and also in searches for new physics, for example, in the anomalous magnetic moment of the muon. We can only do these searches if we can believe the precision that we're getting from lattice QCD. So we need to do lattice QCD tests in arenas where we don't believe new physics is present at a level of precision that we can then translate into these new physics searches calculations. And of course, we need precise experimental results to compare against. So these precision tests are possible where we can bring precise lattice QCD and precise experimental results together. And the ground state heavionium mesons, the E to C, the J psi, the E to B, and the upsilon can provide such tests. And I'm really talking about very high precision here. So, you know, percent level tests of QCD that you couldn't achieve, for example, using perturbative QCD and collider physics. You know, you're just not at that level of precision test. So, so we're able to do that now with lattice QCD when we include QED effects, and that's what we're doing in these calculations. So the results I'm going to show you come from calculations from HPQCD, this group here led by my student Dan Hatton. And there are a few papers over 2020 and 2021. So how has it been possible to achieve this high precision? There are a few ingredients that go into it. I'm not going to talk in any detail about lattice QCD calculations. You've had more discussion of lattice QCD in previous talks as well. So one key ingredient is using a very accurate discretization of the Dirac equation on the lattice. So, you know, on the lattice, we have gluon field configurations, and then we solve the Dirac equation on those configurations in order to get quark propagators. And you have to discretize the Dirac equation onto the lattice in order to do that. And you have discretization errors when you do that. Back in 2006, we developed a very accurate discretization of the Dirac equation in what's called a staggered quark formalism, and it goes under the name of the highly improved staggered quark action, the HISC action. It removes discretization errors through A squared, where A is the lattice spacing. So it's actually the most highly improved action that is being used in lattice QCD. And that has an advantage, particularly when you're dealing with heavy quarks. So we're dealing here with mesons made of charm and bottom quarks, and then it's important because they're sensitive to discretization effects, because they're small mesons and they see the discreteness of the lattice. It's important to have good control of discretization effects for those cases. The second important point, of course, is to have gluon field configurations that cover large range in the lattice spacing so that you can extrapolate well to the zero lattice spacing point. So you can plot out the discretization effects and get to the continuum limit where you want your results to compare to experiment. And so we've got a lot of different lattice spacings that go all the way from 0.15 femtometers down to 0.03 femtometers, very, very fine lattices. And these gluon field configurations include the effect of quarks in the C, so dynamical or C quarks. And the flavors that are included in the C are up, down, strange, and charm C quarks. So all the flavors that you really expect, to have any impact at all there. Bottom quarks aren't included in the C, but it's already true that charm quarks have very little effect. So bottom quarks are entirely negligible. And those C quarks are included, again, using the highly improved staggered quark action. So these gluon field configurations were not generated by us, they're generated by the Milk collaboration. And we've been using them. And so that's actually just a great data set, which enables you then to do these accurate lattice QCD calculations on them. And as I say, it's been important here to test QED. QED effects are small, right? But it's important to include them so that we really are getting as much precision out of these calculations as we can. And we've included QED in what we call the quenched approximation. So that means we've included the effects on the valence quarks of having an electric charge, but we haven't included any QED effects in the C. So the C quarks are electrically neutral, but we expect the main QED effect to come from the electric charge of the valence quark. So this should include most of the QED effects. Now, it's actually quite easy to put in quenched QED, because what you do is simply generate a random photon field and then essentially multiply your gluon fields by it before you solve the Dirac equation. So that is what we do. So let me say something first about the charmonia results. What we calculate, as we said, is we solve the Dirac equation to get quark propagators for the charm quarks on these gluon field configurations. And then we join the quark propagators up to make a meson correlation function, a so-called two-point correlation function. So we put in appropriate spin and colors at the source time 0 and at the sink time t to join this up either with the pseudoscalar quantum numbers appropriate to the eta c or the vector quantum numbers appropriate to the j psi. Now we include these quark line connected correlation functions only. So if you think about the Wick contractions that you could make here by writing down these two operators, you can also have this quark line disconnected correlation function in which these two quark propagators just joined by gluons going across there. Now that you expect to be very small, have a very small effect in heavionium states. We do not include it in our calculation. And then a key question is, what impact does that have? We can test that. It's also important here to note that because we're working with heavy quarks, charm and bottom, actually we can achieve very high statistical accuracy on these lattice calculations. So statistical errors are not an issue here. So we calculate these quark line connected correlation functions over all these gluon field ensembles that we've looked at, with different values of the lattice spacing, different values of the C quark masses, and then we fit the correlators to this multi-exponential form that you'll have seen from lattice QCD. Remember, we're working in Euclidean time, so we have exponential functions with exponents that are set by the masses of all of the states that can appear in this correlation function. Now, the ground state dominates this correlation function if you make this time separation reasonably large, because it's the term that has the largest value for e to the minus mass times t. So the properties of the ground state are the pieces of information that you can get from this fit most accurately, and they're the ones that we are focusing on here. So E0 and A0, where A0 is the amplitude for the ground state in this correlation function, and E0 is the energy of the ground state. But we include multiple states out of this ladder of states in order to get accurate results. for the ground state masses and allow for all the systematic effects that you might have from the inclusion of these excited states. But the results I'm going to show you are for the ground state. And obviously the ground state mass is easily interpreted. For the amplitude, we convert the amplitude into what we call a decay constant. We'll come back to the decay constants later, but that is just simply for the pseudoscalar, it's simply related to the amplitude of the ground state and the ground state energy. And for the vector, it's also simply related to the amplitude of the ground state and the ground state mass. But slightly different formula in the two cases, just because we use a different operator. And it's important to note that the pseudoscalar decay constant is absolutely normalized in lattice QCD when you use the highly improved staggered quark action, because you have a partially conserved axial current that you can use. So no renormalization factor is needed here to match to continuum QCD. But in the vector case, we don't use a current with any conservation relation attached to it. So we have to calculate the renormalization constant ZV to match between lattice QCD and continuum QCD. And we can do that accurately using an intermediate symmetric momentum subtraction scheme. And that's described in this paper here. You do have to take a bit of care over that, but I'm not going to go into the details of that here. Another important point is, of course, that we're working, or at least I'm describing here, charmonium calculation. So obviously we've got to be using charm quarks. And what that means is we've got to tune our lattice quark mass so that it is the mass, the correct mass for the charm quark. How do we do that? We do that by making sure that the ground state vector meson mass, i.e. the mass that we're going to associate with the jape psi, actually is the jape psi mass. So we adjust the charm quark mass in our Hisk action so that we get out the right value for the jape psi mass from each field ensemble. Now, of course, to do that, you need to know what your lattice spacing is so that you can convert from lattice units into GeV units. And we fix our lattice spacing using an intermediate parameter called W0, but ultimately that is fixed from the pion decay constant. So that is all done pretty accurately too. Now, when we do this tuning of the charm quark mass, we use the same tuning for both pure QCD calculations and for our QCD plus QED calculations, because we have two sets of calculations here, so that we're using the same physical tuning in both cases. In both cases, we tune the mass so that the jape psi meson mass is the same in both cases. And of course, what that means is, and I'll show you this at the end, that you can then determine what the charm quark mass is. So we get the lattice charm quark mass from this tuning process. In the end, what you want is a mass in the MS bar scheme. So we then just have to convert it into the MS bar scheme. What is the impact of QED on charmonium? So when you put QED into your calculation, as I say, we're only doing it for the valence quarks, but that should be the main QED effect. You expect two different QED effects. One is a self-energy effect for both the charm and the anti-charm quarks, and that will be proportional to the square of the charge of each of them. But then you also expect an interaction between them, an interaction term from essentially the QED Coulomb interaction. And for charmonium, when you're dealing with a neutral meson, obviously the charm and the anti-charm have opposite electric charges. That is an attractive interaction, and it gives you a negative contribution to the mass. However, the self-energy terms both give you positive contributions to the mass. So actually, there's a net positive effect on the jape psi meson mass when you put QED in. And what that means is that when you tune the quark mass itself, you have to lower the charm quark mass to get the same jape psi meson mass in QCD plus QED as you had in pure QCD. You also, of course, have to recalculate the mass renormalization factor that connects the lattice to, for example, the MS bar scheme, and include both effects in the end. We'll talk about masses later, so I'm not going to go into any details at this point. But the point is that there is a very small negative effect on the charm quark mass coming from QED. The other two quantities that we're going to look at are the hyperfine splitting, that is the mass splitting between the J psi meson and the eta C meson, and the decay constants of the mesons. So as far as the splitting between the J psi and the eta C is concerned, including QED effects, increases the hyperfine splitting by 0.8%. That's not really surprising if you think about how the hyperfine splitting, is appearing in the calculation. Most of that is a direct effect from QED, but there is also sensitivity in the hyperfine splitting too, of course, to the charm quark mass. And so 0.1% of that comes from the fact that you had to retune the charm quark mass lower because of QED effects, and that pushes the hyperfine splitting up. There is also an additional QED contribution in the J psi mass coming from the J psi annihilation to a photon, so another QED effect, and we so calculate that just as an estimate in perturbation theory and add that in. That's a 0.7 MeV effect. So you can see the kind of level of accuracy that we're heading towards, having to include these very small pieces. And for the decay constants as well, including QED, increases the decay constants. Again, that doesn't surprise you because of this attractive QED interaction. You expect, if you're thinking in sort of potential model language, you expect the wave function at the origin to be increased, and therefore the decay constant. That's a very hand-wavy argument. Of course, we're actually doing the calculation here in lattice QCD plus QED. We're not using a potential model or anything else. We're doing a fully relativistic lattice QCD calculation. So results for hyperfine splitting. The points here show the lattice results, and the curve here shows the fit to these as a function of lattice spacing and results at different values of the up and down C quark masses, and this is the extrapolation to the continuum limit. So this orange band here shows our final result with its error. And you can see here that this disagrees with the experimental result here, which is this black line, by this significant amount, which I've called delta. Here's a plot of this, our result here in this blue hexagon, compared to previous lattice QCD results. So you can see we're much more accurate than previous lattice QCD results. They were all, in agreement with our new result, but not nearly as accurate. And this is the experimental value here with some experimental results down here. So what you can conclude from this is that when we include only the quark line connected correlation functions, we see a significant disagreement with experiment. Now, since we're not imagining new physics in this quantity, then we assume that this is coming from that annihilation diagram that we are not including. So this would tell us that the contribution to the eta C mass coming from that annihilation diagram is 7 MeV with an error of 1 MeV. Now, this is a bit different from what you would expect from leading order perturbation theory, but subleading terms could easily generate, you're expecting something like minus a few MeV, and we've actually got plus 7 MeV out of this, because the eta C mass would be increased if annihilation diagrams were included, so that the hyperfine splitting would go down towards the experiment. But as I say, higher order terms could easily produce that effect. Now, for decay constants, we can look at the decay constant both for the J psi and for the eta C, and we can look at the ratio of the two, which we can calculate even more accurately than the separate decay constant. So this is our result in the continuum limit for the decay constant of the J psi. We get 410 MeV with an error of about 2 MeV, so that's 0.5% accuracy. And we get that the ratio of the J psi to the eta C decay constants is bigger than 1 by about 2%, and it's a 0.2% accurate result. For the J psi, we can translate this decay constant into a value for the leptonic width of the J psi, and we can compare to experiment, because this leptonic width is known accurately from experiment. It's this gray band here, and here is our result from this value for the decay constant. And you can see that our result agrees well with experiment. It's actually more accurate now. The lattice QCD result is now more accurate than the experimental value. So an improved experimental value there would actually be good. And we can extend calculations to bottomonium by increasing the quark mass up from charm to bottom. Now, we can't just go direct to bottom because the bottom mass is so big that it's actually difficult to reach on the lattices that we use without having big discretization effects. So what you actually have to do is do a lot of different heavy quark masses going up from charm on lots of different lattice spacings, and then fit all of your combined results as a function of lattice spacing and quark mass in order to then get a result at the bottom. So for example, here are the results for the hyperfine splitting between a vector heavionium meson and a pseudoscalar heavionium meson as a function of the vector heavionium mass. And we've got lots of different lattice results here that we fit to a smooth curve. In fact, we use a model independent cubic spline to do these fits. And this is the purple curve here. And then we fix the result that we want at the bottom mass by the point where the vector heavionium mass is actually equal to the upsilon mass. So that's the tuning for the B quark mass that we do here. So that you can see we get an accurate result for the, it's not as accurate as in the charmonium case, we get an accurate result for the bottomonium hyperfine splitting of 57.5 MeV with an error of 2.5 MeV. So this is a huge improvement on previous lattice QCD calculations. And this is a comparison of our results with the experimental values that there are. This pink band here is the experimental average, and we agree well with the experimental average. This blue band carries our result down for comparison, but we agree particularly well with the most recent experimental determination of this hyperfine splitting that comes from the Bell collaboration. Now here, notice that we are not seeing any discrepancy that would imply an effect from those disconnected diagrams, because the disconnected diagrams are not included here either. But we expect in perturbation theory a much, much smaller contribution, and we expect the perturbative estimate to be more correct in the bottomonium case than it was in the charmonium case. So we simply take a 1 MeV uncertainty because of that in this case. And as I say, we see good agreement with experiment. QED effects are much smaller here because the bottom quark charge is only a third. So we include QED effects, but they have basically no impact. And here's the results for the decay constant of a vector heavionium meson, plotted as a function of the heavionium vector meson mass. So you see you get the mass dependence as well from these calculations, as well as the results at charmonium and bottomonium. And this is our result for the upsilon decay constant, 677 MeV. And what we see, interestingly, when we look at the ratio of the vector to the pseudoscalar decay constants, is that it actually falls through 1 as you go from charmonium to bottomonium. So it's larger than 1, as I showed you for charmonium, but it drops below 1 for bottomonium. And we can calculate again the upsilon leptonic width from our upsilon decay constant and compare to experiment. So here's our result here in blue with a decay width of 1.292 keV. And here's the experimental average down here. So now we're not as good quite as the experiment, but we agree well with it. And again, big improvement in accuracy over previous lattice QCD results. So let me say something very briefly about the determination of quark masses from lattice QCD. As I've said, for the charm quark mass, we tune the lattice mass from the J psi meson, and then we determine the mass renormalization factor that will convert from the lattice scheme to the MS bar scheme via a symmetric momentum subtraction scheme. Again, you have to be a bit careful doing that, and we've done quite a bit of work on that, which you can read about in those papers quoted up here. And we've also included QED effects now. And as I said earlier, the combined impact of QED is a very small negative effect at a scale of 3, when you've converted fully through to the MS bar charm quark mass at a scale of 3 GeV. So here's our results for the charm quark mass now in lattice QCD plus QED compared to earlier lattice QCD, pure lattice QCD results. So, you know, the effect is very small of QED, and we get good agreement between at least all of these lattice QCD results, which are all now very accurate. We're down at less than 0.5% accuracy. For the B quark mass, what we do is to calculate the ratio of the B quark mass to the charm quark mass through calculating the ratio of a heavy quark mass to a charm quark mass as a function of the heavionian meson mass in pure QCD. Let me just show you the plot for that. It's here, and then we read off the ratio of the B quark mass to the charm quark mass at the point where the heavionian meson mass is equal to the upsilon mass, and that tells us what this ratio is. Now, we can do that in pure QCD straightforwardly. When we want to put in QED corrections, it's more tricky because the charm and bottom have different electric charges. So you have to first calculate how the ratio is affected by QED in the case where you take the charges to be the same. So we do that for the two quarks both having a charge equal to that of the bottom quark. It's a very, very small effect. And then we have to correct for the fact that in the ratio, the charm quark mass has therefore been given a charge of 1/3, which is not correct. We want it to have a charge of 2/3. And so using our results from our earlier charm quark mass calculation, we can adjust the charm quark mass from an electric charge of 1/3 to 2/3. And that finally gives us the ratio of the bottom quark mass to the charm quark mass in QCD plus QED here, very accurately determined. But notice this has to be now given at a fixed scale, because obviously if you run the scale, the charm and bottom run differently under QED because they have different electric charges. Here's a plot of the bottom quark masses comparing different lattice results. And again, we now have really very accurate bottom quark masses from lattice QCD. So my conclusions are we've reached high precision as we wanted to for the ground state properties of the E to C and the J psi, and we're now including QED effects. We see this effect in the hyperfine splitting from gluon annihilation, the E to C annihilation to gluons. And we have calculated the J psi leptonic width very accurately and able now to compare that to experiment. And indeed, it's more accurate than the experiment. We've extended the calculation to bottomonium, again, using this fully relativistic, highly improved staggered quark approach. And that enables us to get more accurate hyperfine splitting than before, and also an upsilon leptonic width. And we've determined the charm and bottom quark masses very accurately as well. So the future is that we're going on to accurate determination of other decay modes that can really test QCD accurately. So for example, J psi to E to C gamma and E to C to gamma gamma. We need more accurate experimental results there. And we're extending these accurate determinations of heavy light meson, of masses to heavy light meson masses. So this is all then background to our program of calculations of semi-leptonic form factors for weak semi-leptonic decays, where we're searching for new physics in the comparison to experiment. Okay, thank you very much.
Thank you very much for your talk, Christine. Now we are open for questions. Let's see if there is some hands up here. One, Christoph.
Thanks, Christine, for this excellent talk. I enjoyed very much. I have a question regarding this hyperfine splitting in the CC bar sector.
Right. Should I go back to that?
When I got you right, you started this program to understand how accurate one can really control these lattice QCD calculations. But now you see a deviation and just attribute it blindly, so to say, to something that you do not calculate. So that's not really an accuracy test, because you cast everything.
No, you're right. You're absolutely right. No, of course, this could be new physics, right? That would be more exciting.
No, actually, there's something else I wanted to aim for, because we've heard this talk on the G-2 contributions.
Yes.
And there seems to be some problem eventually with the lattice systematics. That's especially in the discussion session Christoph Löhrer alluded to. And can you exclude that there are any systematic effects besides the annihilation that could also influence your result here?
Well, as you can see, we've got a pretty complete calculation in this case. You know, we've got lots of different lattice spacings. We've got lots of different results for the masses of the up and down quarks in the sea. And so it's difficult to think of any other systematic effects. So that's, you know, partly why we're driven to this conclusion. I mean, of course, it's also true that you do expect an effect at the few MeV level coming from the E to C annihilation. And so it's not surprising that we see such a thing. There's been a lot of controversy about the sign of the effect. The perturbative sign is negative, but there have been other lattice calculations. I mean, you can't do the full calculation in lattice QCD because it's because E to C annihilation to gluons then introduces a whole load of other states, you know, glue balls mixing with the eta and eta prime and so on. So to actually do any kind of direct calculation of this effect is at the moment impossible in lattice QCD. But some quenched QCD calculations had implied that there was a positive shift coming from mixing between the E to C and glue balls, which is all that's allowed in that scenario. So there was controversy already, you know, about the sign. So we were expecting a few MeV effect, and we would assert that our results demonstrate that that effect is positive and of the size 7-foot MeV. But you're right that we haven't directly calculated it. So if there was some other systematic effect that we haven't thought of, it could be having an impact here. But of course, we have also calculated the decay constants, and with the masses, right? They're coming out of exactly the same correlators. So the decay constants come with the masses, and there we've got a very good agreement with the experiment for the leptonic width. So I think that shows that we have good control of the systematics. And also the charmonium and the bottomonium calculations go together, right? You know, that once you've done one and you push the mass up, you know, you're heading towards the other calculations. So they are clearly connected together. And in that case, it's not as accurate, of course, but in that case, we do get good agreement with experiment when you expect the annihilation contribution to be much smaller. So the picture is a completely consistent one.
Okay, thank you very much.
But I, you know, I agree with you that you know, there is a bit of an assumption in there that is where that difference is coming from.
Thank you very much. Are there more questions for the speaker? Very shortly.
I should say as well, you know, carrying this on to look at heavy light meson masses at this level of accuracy will also test the systematics as well. So the idea is to get a more complete picture of all of these ground state properties at a very accurate level. And then I think what will be true, you know, is that the only hyperfine discrepancy with experiment will be that charmonium one, and then we can be clear that it's coming from the E to C annihilation.
Can I ask one more short question?
Yes, and then Biplab also has a question. Please go ahead, Christoph.
If you want to do the J psi going to eta C gamma, but your hyperfine splitting is not accurate, how do you want to do that then?
Well, so then you do have to be careful and take an uncertainty from the fact that the kinematics on your lattice is not quite right. Yes. So that's, I mean, we have some results. We don't have a final result yet because we are worrying about issues like this. Yeah.
Okay. Thank you very much.
Okay.
It's not a big effect, but you're right. You know, it obviously affects the end point of your calculation.
Biplab has a question, and also Claudia. Biplab, go ahead.
Yeah, I have a quick question about this last remark. So this is basically you are positing this as a validation of this HISC formalism for these form factors. Is that the idea?
Well, for lattice QCD in general, right? I mean, it enables us to be clear that when we say we have an error of, 1 MeV or 1% or whatever, that we really do.
Okay, thanks.
And Claudia also said the last
Well,
one.
my question is sort of related to the two previous ones. How much your tuning on the JPSI mass or on the splitting is sort of a circular internal, because you're always working with the ground state charmonium. So I'm worried that you are sort of underestimating the lattice error, because you're working in the same system with the same kind of transition. That's what.
So sorry, you're worried particularly about JPSI to E to C gamma.
And eta C to gamma gamma, because you're sort of, I'm not sure how much the quantities that you are using to, that you want to determine with accuracy are independent from the fine tuning that you do on the mass.
No, all we're doing, we're not doing any fine tuning of the mass, right? We're just tuning the charm quart. You have to tune the charm quart mass somehow, right?
Yes, but you are tuning on the quantity.
The charm quart mass is that mass in lattice QCD that gives you the right JPSI meson mass. That's the way we tune it.
That's it. But what I'm saying is that you are tuning it to the JPSI mass.
Yes, yeah. So that we have, so the JPSI mass is defined.
But then you are predicting something which is also very strongly. I mean, what I'm saying is that if you were to predict something, for instance, I know that it's difficult to go to the radial excitation because it's completely difficult, but you are always at the same scale. Basically, you're close to the scale to which you are tuning. That's my. I'm not saying
look at
it's a concern.
The point here is the accuracy, right? We're calculating.
No, I agree with you, but what I am saying is that I'm concerned that this accuracy might not be so large when you go farther from the point where you tuned it.
Oh.
That's my worry. That's what I would like some reassurance from you.
This is a very small splitting, hyperfine splitting, and that's part of the reason why we're able to do it so accurately. We can look at radial excitation, or we can look at the first radial excitation, but the accuracy on that won't be as good because it's a radial excitation. So, the reason for focusing on the ground state properties is to get this very high accuracy. But where else could you get this accuracy from, right? You can't do any other, there's no other way that's going to tell you.
I agree with you, but my worry is that extrapolating from this very high accuracy on a small scale of the parameter is good. I believe that you trust your gamma width. But what I'm saying is that when you go farther from this,
I know, but we don't, right? I mean, the semi-leptonic form factors are all ground state ones that we're trying to do accurately. So, our collaboration is called high precision QCD collaboration. And we focus on accurate ground state properties. So, this provides the underpinning for form factors, for example, for BC to JPSI decay that we calculated recently.
Yeah, but then you need to go also for the G-2. That's the.
Yeah, no, we have done G-2. I've actually got a spare slide here on the charm contribution to obviously the charm contribution is small, but you can calculate it incredibly precisely. We calculated it back in 2014.
Stop and we move maybe this in the afternoon discussion.
Right.
30 seconds, and then I must
stop sharing then. Yeah. Yes.
I'm sorry.
No, that's fine. Thank you. Thank you for the discussion. Yeah.